So welcome, Professor Paradiso, and thank you for being here. We're looking forward to hear your presentation. Thanks a lot.
Thank you very much, Luigi. It's really an honor to be back here in Recanati again. Such a wonderful place, just a beautiful location, and so much interesting work happening here. I mean, to seeing Italy's commitment in clean energy and going green at every level is just impressive. And the things you guys are rolling out for smart infrastructure for that are really the right way to do it. Again, it's a true pleasure to be back in Recanati. I've been here now a couple of times, and it's just in such a beautiful part of Italy, and it's so fascinating to see all the great work that's happening in the industry and the universities and the research infrastructure. It's a wonderful place. So it's my honor to give you this talk. I'm going to talk about a lot of projects that I'm doing at the Media Lab. I'm going to go through them very quickly, but I'm going to, at least in the first part, concentrate on building control. This is an outline, more or less, of what I'm going to try to say if I have enough time here. I'm going to start with a little bit about the MIT Media Lab. Probably some of you have heard about it, but I'll give you a little bit of orientation to kind of ground you on what the lab is about. I'm going to have a little bit of talking about the MIT Zero Carbon project. I'm part of it. The work I'm going to show is not really my own work, but I work closely with the people that are doing this, and I'll orient you a bit to that. The other stuff is all stuff I'm doing in my group. So a lot of stuff on wearables. We're one of the leading groups in the world on wearable sensing research. We've done work on adaptive HVAC, adaptive lighting, environmental sensing, all for the built environment. So I'll talk about that. If I have time, a little bit about e-textiles, what we call Sensate Media, which is an extreme version of that, cross-reality, digital twins, and AI and user modeling. So it'll be a lightning tour. This is all related, certainly, to the built environment. This is too, but not quite as directly in every case. So I will entertain you. I think after a long day of talks, it's my duty to entertain you, so I'll do my best. So yeah, the MIT Media Lab. This is what it looks like. We're in the corner of MIT here in the East Campus. This is our building. It's only about 10 years old, designed by Fukihiko Maki. Beautiful building, all glass. It's just a wonderful place to work. And what goes on in there is equally as spectacular, at least to me. It's a very special place. It's special, I think, in many ways because of the freedom. We're free to imagine different futures and incarnate them. We take funding coming in from different sources. A lot of it comes from industrial sponsors, but we don't do directed work. We don't take a directed project unless it's something that we really want to do as part of our research. So that lets us dream and come up with things that are unusual that wouldn't be in the course of what a market would anticipate. So we tend to be ahead. If anything, we're an early warning system on the future. So we like to think about what the future is going to be and then work to build a piece of it, right? We emphasize building. Theory is important, we're academics, but we really want to build a piece of this future you're talking about so we can experience it. The whole demo philosophy is very important for us. This is another critical thing. We're very interdisciplinary. So the MIT Media Lab has got 35 researchers that are from very different disciplines. Somehow we all talk together and ideas come in between these different domains, and the students don't even care about the domains, they all collaborate. So that sparks a lot of innovation. So it's very electric with all these different perspectives clashing. And again, we have member companies that come to visit, colleagues come to visit all the time. All kinds of visitors. So opportunity abounds. There's always a distraction of some sort that's really interesting. So we're getting pulled always into a different mode of thought. This is a slide I made in 1998 trying to figure out how the Media Lab worked. We don't have any kind of real org chart. But these are the different disciplines that were there at the time. Similar now, we have a lot more bio happening now. We have people doing genetics and gene drive and things like this. E-markets is now digital currency, so it's changed a little bit, but it still has this wealth of different disciplines, all in close proximity, and students and member companies coming in and collaborating and picking ideas up somewhere and dropping them off somewhere else. So it's a wonderfully interdisciplinary place. It's special for me because of the way not only do disciplines meet, but different modes of inquiry meet as well, right? So certainly we very steeped in engineering. We do a lot of it. We're part of MIT and our engineering, it goes as deep as it goes. As well science, especially in the bio groups now, we take science very seriously. But then we also have a tradition in art and design, which is also very important for the Media Lab, very important to me as well. So we have, thinking that you may get in art and design, not unknown in Italy, where you go very deep in these areas, but combined with deep science and engineering. So the Media Lab, we go across this. This is something that my colleague Neri Oxman developed based on the Krebs cycle of how bacteria metabolizes nutrients and recycles it through. We do the same thing with ideas. She had an earlier version that was a little crazier. So she has metaphysics in there and who knows whatever else. But again, it's the whole idea of different perspectives coming together and really making something larger than what they are individually when they assemble at the Media Lab. On the left is the way we've evolved topically. We started as the Lab for Convergence. So in the 1980s, media convergence was not a commonly accepted idea. The lab started in 1984. Nicholas Negroponte, our founding director, came up with the term convergence for print, publishing, broadcast, film, everything coming together in one platform, which really is the computer, basically. That was not intuitive then. We live in that world now. So after that, we evolved more into Internet of Things. We did a lot of fundamental work in IoT, where we looked at it as atoms and bits and people coming together. And now it's more brain, body, and technology, right? And brain is something that's harder to define as something that stays in your head, right? We can connect to AI. Brain becomes something much, much bigger than us. And how does this all join? The Media Lab is very much about that question now. If we're about any topic, it's how we connect to this world outside in different ways. That's the thing that's most in common with all of us, actually. So getting back to my group, in particular my research group, we work at different scales. We do a lot of work in wearable computing, have for years. We're very well known for our work in wearables. We do work a lot with the built environment. I'll give some examples of that, lots of different projects. We do a lot of work too with environmental sensing. That's a whole separate talk. I won't have time to go into that now. And I'll say a tiny bit maybe about space, but won't really have time to talk about it. We have more and more projects that actually are being launched into space now. The Space Initiative at the Media Lab is headquartered in my group. I worked in spacecraft control for years. So we've got work that's actually being deployed and landing on the moon. We have a little payload landing on the moon. And the next lander, which hopefully doesn't fall over, will stay upright. This is my research team. We have up to 20 people, maybe more. We have visitors that come from all over the world to spend a semester or do their degree in my group, as well as my own MIT students. And it's just a wonderful group of innovators that are very deep technical engineers, scientists, but also a lot of them are musicians and artists of different sorts. So the Media Lab brings all that together, and my group really celebrates that concept. So, on to energy. This is a screenshot of MIT's En-ROADS. Any of you know that? It's a great package. It's done by the Sloan School, not by the Media Lab, done by MIT Sloan School, people that do operations research, basically. And it's a way to trade off different kinds of scenarios for conversion of energy in different sectors and see what greenhouse gas temperature you will get to by what year. So you can see what goal you make, and you can play with it just by sliding these sliders. It's a wonderful tool, very intuitive, and it's very effective, and you can drill down even deeper than this. I have the URL in the next slide. One thing that is consistent when you play with En-ROADS, and it's something Luigi and I have been talking about, and it's something I've heard today actually over and over again, it's tough. Well, I'll talk about it in a second. All these new technologies take time to scale. I'm sure a lot of you know Antonioni's great movie, Deserto Rosso. One of the first films about environmental catastrophe. I don't know if there's one before that. I mean, it was before people knew about global warming. It was about more pollution. A very moving, beautiful, artistic film. And this is not the kind of world we want to live in. Now it's all about, rising temperatures. Pollution still plays a role. But yeah, we don't want to live there. So we want to move away. But again, if you look at these things we can do in En-ROADS, safe increased renewables, safe fission reactors, fusion, maybe extracting CO2 from the air, whatever else, there's not enough time to scale them. Even the opportunistic scenarios, there's not enough time to roll them out at scale to really help prevent significant warming and stay within guidelines. It's one of the clear things you see when you play with En-ROADS, for example. So we have to think more broadly. Okay, geoengineering, fascinating idea. You know, spraying diamond dust or whatever else in the atmosphere, other things you can do to try to cool the planet down. It may be a stopgap. We might have to do it, right? So I think it's important that we know a little more about what we're doing if we ever have to get there. Hopefully we don't. Neil Stephenson, famous science fiction writer, I've actually interviewed him a few times at the Media Lab. He's a great guy, but he wrote a novel, Termination Shock. Did any of you know that? It's one of his last novels. He's probably the best known of the cyberpunk authors. He invented the word metaverse. But his last major novel is about climate change and geoengineering, where basically something happens to civilization where you stop spraying the dust, stop cooling the planet down, but you've been dumping CO2 into the air since, right? Because it's not fixing the problem, it just gives you a stopgap. And of course the Earth within months just warms up tremendously. It's a rapid road to a catastrophe. So yeah, there are issues with this, but it has to be in our pocket. But this is what we can do. We've got to turn the dial down on energy. We've got to lower our energy use in the interim before we can roll out these other technologies. And it's clear if you look at any of the forecasts, that's really important. For those of you who want to play with En-ROADS, this is the URL here. And the question is, how do we do it? I'm going to give you a few examples by what we're doing at the lab. There's one branch of Internet of Things that's related to that. It's called persuasive computing, not pervasive computing, which is more IoT. Persuasive computing. It's in computing environments that convince people to do certain things. It's what you see in social media, not for the good of humanity. But you can think about it for energy. Convince people to, you know, lower their energy use different ways by real-time intervention. It's been an idea, it's been around for a while. I edited a special issue of IEEE Pervasive Computing. It was the main journal for Internet of Things at that time. And it was about smart energy systems. And I had a great article by a bunch of friends at Microsoft Research in the UK about this. And the whole scenario is it's very hard to do. It's really difficult to convince people to turn it back. I see it at home. I've worked a bit in the energy sector. I know what demand response is. When I see that symbol on my Nest, that little gear, demand response, I feel good. Even though I'm uncomfortable, I'm helping the environment because the utility is basically having me suffer a little bit to save energy in a peak moment. My wife does not like it. She hates it. What are they doing this for? So there have to be different approaches for different people. I think that's going to be important when we get into this thing. But yeah, I think we have to use smart systems to throttle energy as mandatory. Our hands have to be taken at least directly off the thermostat. Most people don't even know how to use thermostats, right? They pin it up one way or the other. It's got to be, our hands have to be off of it. And we're seeing the beginning with smart thermostats. We can go a lot further. So I'm going to talk a bit about MIT programs. MIT has a carbon reduction goal for campus. They've just announced it like a couple of years ago. They want to eliminate direct emissions from the campus by 2050. So no direct emissions at all. And net zero by 2026. It's the goal. It's all really soon. MIT campus is significant. It's close to a square kilometer, and it contains 205 buildings. A lot of them are old with old HVAC systems too. So it's a tangled mess that has to be untangled before we can start to use techniques to do this. So I'm part of this team. It's being led by Christoph Reinhardt, it's professor in building technology, old friend and collaborator, and Julie Newman, who is in facilities running sustainability. So she is the person who works on implementing this across campus, and she knows all about sustainability. She's wonderful. So she's the person who really gets it done, and Christoph is the academic, the researcher. It's really a great combination. We have a chance maybe of doing something. One of the things we've done as part of this is run a class. This is Christoph's idea. It's decarbonizing the MIT campus. These are students from programs all over MIT that took it. And there's a list of lecturers. I gave a talk, so that's me. But you know, people that are playing in this field, some of the people, different parts of MIT. Actually, this is Les Norford. He's one of MIT's authorities on HVAC. I'm going to talk about his work in a minute. There are 3 outputs that came from it. There's a presentation, which I took some of these slides from. They did a report, and then they have a dashboard you can actually play with, like with En-ROADS, and try different things for the MIT campus to see what the effects will be. If any of you are interested, there is links to the documents here. And again, this is stuff we've been hearing about all day. They looked at different technologies, stuff you can do now, things that could be implemented in the future, and the stuff that we really can't control directly. And they separated them out and then tried to adjust these things we can do. So this is some of their results. MIT has a physical plant that basically burns, I think, natural gas at this point. We can produce some electricity. We definitely produce steam, and steam heats and cools most of the campus, actually. It circulates across a good part of it. Again, it's mix and match. You have different kinds of systems in different places, but the steam is involved in most of it. If we just looked at what the grid's going to do by itself, assuming natural decombination of the grid, we get about a 5% reduction by 2050. It's not great. Don't want to rely on that. Rooftop photovoltaics, retrofitting the buildings so that they're more efficient, and then doing the kind of smart control things we're going to talk about in a minute, where you have the thermostats and the systems try to heat and cool less depending on context. The students predicting that we're down by about 45%, so that's significant. And then, going a little bit further, right? So we can electrify the heating. We use heat pumps. We have borehole fields where we can store heat down to 200 meters in the ground, and do other things of this sort. We get pretty close. The current grid there, if the grid is decarbonized, it's even more of a savings. And then you can go further. Nuclear batteries, I'm a firm believer that nuclear power will come back, even as fission, before we get fusion working. They can get you down there, or in deep geothermal, go down 20 kilometers into the ground, right? The people are working now on drilling at this level commercially. So this will essentially get us there. Or carbon capture, right? In the actual plant we have now, there are ways to do it. It's a little complicated, but that gets us there too, potentially. So, what about this? What about this? Man, of course, a technical kid always was wondering, when are we going to see real AI? I'd never guessed the answer would be 2022, 2023, but it happened, right? By emulating brains with these connectionist deep neural nets, we basically have what we dreamed of as AI. What kind of AI is it? We could argue that the whole hour. But it's intriguing. It's a breakthrough. It's a different world. The world changed. Is it the singularity? Not really, but who knows what the future is going to be. But people have been predicting this for a long time. So this is Norbert Wiener. Some of you have heard of the Wiener filter. It's before the Kalman filter. It's a standard estimator that everyone learns in engineering school. He wrote the book on cybernetics way back then, one of MIT's legends. And one of the more notorious, less reputable newspapers in Boston took a quote from him, basically saying that thinking machine is seen replacing man, already in 1949. In unskilled labor, he's looking at unskilled labor being obsolete. Who would guess it's potentially the creative industries or the knowledge industries that are kind of under fire now. But MIT, we don't believe in replacement. That's the wrong way to think. Any technology, when it comes in, it has opportunities as well as has some detriments. And we see thinking machine extending man. And all the work that we're doing with AI is trying to extend human capability through AI. I think that's the really exciting thing, and we're at the edge of what that can be now. So it's great. And in building systems, this is something that I think is certainly relevant. So we see, at least I see buildings as evolving to be prosthetics extension of people. Maybe symbiotic is a better word, but we like the building system to kind of be an extension of my sense of comfort, and something that lets me see, lets me basically navigate through an indoor environment in a way I want to. Almost the way a prosthetic would help somebody walk if they lose a limb, right? An extension to the human. It has its own aims. It wants to save energy, but it also wants to attain your goals. How can we do that with the smart systems we're developing? This is a project we did, the first thing we did in this space, 2008, 2010, way back. It's my former student Mark Feldmeyer's work. And we're thinking about a system where we have sensors in the infrastructure, sure, but also wearable. And that was kind of crucial because that's the first person perspective. That's before you had watches or even activity monitors. You know, wearables at that time were kind of big clunky things. But we figured, okay, let's put a wearable into this, and let's have it measure at extremely low power. The battery, the coin cell in this actually would have lasted months, if not a year. Mark claimed it lasted a year. So we integrate the vibration using a very low power analog accelerometer, measure temperature, we measure humidity, light levels, things like that. It really, microwatt, nanowatts. And the critical thing with this is you can label whether you're comfortable or not. It had a blue button and a red button. You could label if you're hot or cold. We had our own little low power wireless protocol, so we could tell if you're in an office, and every so many minutes it would upload the data to the server here. And then we had some infrastructure sensors. This is our low power accelerometer. For those of you who are engineers, we did it all with analog integrators. Very, very low power, nano power amplifiers. Now digital accelerometers are very low power. It didn't exist then. They were all accelerometers were too power hungry, so we made our own with a passive one. This is working as an activity monitor. It worked. We also took over the dampers and the HVAC, so we could open and close the damper to change the air conditioning load. We couldn't get into the physical plant. MIT now will let us get into the HVAC and send commands to it, because it's such an important priority. Back then, we couldn't even touch it, so my students hacked it with their own little motor. And we measured airflow here. We could open and close a window, same thing, right? If it was better to do that. Sorry. Oh my God. How long has that been going on? Thank you very much for alerting me. So we could open and close windows. And in the end, this is how we controlled it. Here's where people said they were too cold. Here's where people said they were too hot. It learned a personal comfort model for each individual. And basically, in this case, it separates out nicely in enthalpy space, almost with a line. So we could decide to cool over here, you know, potentially heat over here, at least adjust the HVAC, depending on your personal curve. Yeah, this is getting into something that still is important, comfort, right? You can put sensors in to measure lots of things, but inferring the sense of comfort of individuals is still a frontier. We made some progress here. There's a lot more to do. Actually, we've been talking to a group at the University of Macerata. Paula's group was really interested in that for a while too. I think it's still important, and with AI, we can do even better than this. So yeah, this is during a summer, same conditions across. People were less comfortable before our trial, and we just had the thermostats. Everyone's usually too cold in buildings at Boston. And we used our system. People feel better. They're more comfortable, and we use less energy, much less. We estimated it from the chilled air, so much less chilled air. We estimate about a 25% energy reduction at the plant. And of course, the question everyone asks, what about multiple people? So you can do what you want, because everybody had one of these. We had about 10 subjects. And if they shared an office, here's a case where two people shared an office. This person liked it warmer, this person liked it cooler. And when the person who liked it cooler came in, it turned on the chilled air. That person left for a significant time, it turned it off, comes back on, and it turned it on again. It tries to minimize the aggregate discomfort. This is the comfort metric here. We could make one person have a stronger preference than the other, right? I mean, but we used just an average in this case. This is work from Les Norford that kind of continued on to some aspects of this. And actually, we're starting to collaborate with this group as part of this MIT Zero Carbon program. Les, again, is professor in MIT Building Systems, and collaborated with Prior Dante in MIT CCEL, Computer Science. And the whole idea is to, again, use a system that's occupancy and weather driven. It basically forecasts set points and uses machine learning to figure out, you know, what people's schedules were, the optimal use of these classrooms, and try to maintain thermal comfort. He used something like a PMV here, predicted mean vote. But they put this together. They have it in several phases. The first phase, they've got 24-hour look-ahead set points, and they're looking really at classrooms for the most part. And then they're going to start integrating comfort and other things as they go. And this is a block diagram of their stuff. It takes in all this information from the sensors to, again, look at occupancy and people flow and weather. That's not so unusual now. But they have basically deep neural nets, and they learn patterns of activity. They also have a room model that they incorporate, and they work all of this with reinforcement learning to keep refining the model over time. So this is the kind of system that's going to be just common as we roll it out. But at MIT, we've done it in 6 classrooms. This is pretty much what I said before. And they saw a reduction of 38% in the 6 classrooms they ran. Again, just with smart occupancy models. In offices, it's a little bit less efficient because the usage pattern is different. People are in offices more, but they saw a 12% reduction. So again, just in this early pilot, we can save significant energy just by using sensors and doing it in a smart way. And it's just the tip of the iceberg. I'll be working with them on better comfort models, wearables, even this thing, this watch. You can do a lot of what we did in our old one. So yeah, we'll do that. So moving on from HVAC, we've done a lot of work in my group on lighting, and it's intriguing because this is the lighting controller in our 10-year-old building. Nobody knows how to turn the lights on. It's a Lutron controller, it's a bunch of faders that do some things, and there are set points, and I don't know how to use it. I push a button and try to find something, and usually it's the wrong thing. So we thought, okay, already a long time ago, let's build a sensor that can see how much light comes from different fixtures because you can modulate them. And then a simple linear program will set up to optimize the lighting anywhere. So you put this thing down almost like an artificial light source, and it sees how much light comes from what. It does an energy optimal balance of light coming in so you get what you want where you are. You can have a slider to dim it up or dim it down. And then what about a wearable? Same idea, look at reflected light. So wherever you're looking, look at the light that comes into your eyes and adjust it, because we know how much light comes from each luminaire, because they're modulated differently. So we did it using the sensors in Google Glass at that time. And we also went beyond just the linear program and leveraged context. So we saw how much light was coming into your eyes, but also we could detect what you were doing and adjust the lighting for that. And we had a whole set of lighting trajectories that we did with principal component analysis. Basically, we had people rate a room lit in different ways, essentially the room that we were working in, and then we could find principal axes to it that were natural transitions for humans, the way you want lighting to change, right? And it involves washes as well as illumination and color, temperature, all of that together. And it's counterintuitive, but it's natural. You see it along these axes, it makes sense. So yeah, different way to adjust it. So here is Nan Zhao in her office with this system running. She's wearing, again, glass, using the sensors in glass. And as she's moving around, you'll see the light change so that she gets more light into her eyes if she is in an area that's dimmer. So it's adjusting automatically. And then she's on the phone and knows she's being social. It detects that. So it fades into a setting using these axes that's better for her social. So we had axes from social to work, and we faded there. And then she goes back to work. It goes more into a cooler setting. It's better for that. And then a colleague comes in. My students are all musicians, especially at that time. And it detects that she's having a conversation, she's being social. It goes into that lighting automatically. So yeah, who needs a light switch when you can leverage context? I could even find the light switch. I mean, Louise, in your house you have wonderful light switches. I don't know which one does what, and I have to experiment and play. It should happen automatically through context. But going further, what if I can bring the essence of another space into my place, right? So not just change the lighting, but bring me to a place that's important to me. It could be the library if I want to focus. And we still have libraries at MIT, the books are going away, but the libraries are great places to work, but I can bring the library to me too. So we built a room with large back projection that we could basically have video from anywhere on, and we could change the lighting together with the projection and do it all, essentially like what you have in TV systems now. But we could bring the room everywhere and not just do it on command, do it according to how people respond. So we had sensors on the users that would basically detect their effective state. We want them to be ideally restored, relaxed, and focused if they're working. You want to be at least in these coordinates in this corner. And we could detect it from the sensors and by looking at their face and have the room automatically be, again, like a prosthetic. It's helping people be focused and restored, helping them ideally be more productive. And these are the sensors that we used in this test. So here's an example. Somebody has a lot of time on their hands. So, they're at work, but they're looking at cat pictures or something. We all do that. And then their day got more complicated. Something happens. This happens to us too. And they got more work dropped on. They're stressed out. The sensors detect it, and the room will bring itself into a mode that for this user is restorative. So for him, it's the woodland setting. It can be different for everybody. So he feels more in control, ideally, and he gets to work. The system detects that, and it brings him to the library, which for him is better for flow, essentially. So room is partner, where it really can transform itself to put you into the right state. It can try to minimize energy while it does it too, but the whole idea is to affect the user. That was all open loop. Everything is working, we didn't close the loop. Here we close the loop. So this is her current state. She wants to get up here. We reweight the images, change the images to find one that works, and then she ideally converges. So it adapts. It will adapt to people, because everyone is different. It learns from them. We made a portable version. We work with a lot of our industrial partners. We've worked for years with Steelcase. They give us a lot of their furniture systems, the new things that are coming out to reinvent. So they had a portable desk, and we augmented it with scent displays, as well as the projection, thermal control, sound with headphones. It could even, again, do scent. And you can move this anywhere. It's portable. So they built 3 of them. 4 of them brought it back to Steelcase, and they've done R&D and based some of their product development on this. We have a program in Shenzhen as well. I mean, some of you work with Shenzhen. I mean, you're active in industry. That's a great place to get things manufactured. It's a city just dedicated to grassroots manufacturing. If you when we bring our students there, they're exposed to this, and it changes them. They learn how to make things at scale. And we had this idea of making glasses, not a smart glass display, which lots of people work on and certainly is going to get better and better, but rather glasses as sensors, to look inward at your affective state so you don't need all these sensors on you, as well as look outward at the environment that you're in. So one thing that intrigues us is cognitive load, right? How cognitively loaded are you? And it turns out if you measure the temperature at the bridge of the nose and the temples, the difference relates to cognitive load. It's known in thermal images, and we can do that with thermopiles that we put on the glasses. So we embed them in the glasses, and they measure the temperature around the head at these places. And then we can measure other things. We look at head motion. That's easy with an IMU. We can even track you quite precisely with a little bit of infrastructure, look at eye dynamics, and we can light the glasses up. We use them a lot for distraction studies. How focused are you? We can tell when you see a color change. The sensors are working. The cognitive load, thermopiles, the thermopiles are working quite well, and there's information that's useful in cognitive load. By themselves, I think they're not enough. We have to ground it with other data. But it gets us partway there. And then, look, we're living in dirty environments that have a lot of, effluents, particulates, all kinds of other things in the air. Why can't we measure that? The first time we did it was with ENEL. We had a contract with them when they were refurbishing nuclear power plants in Slovakia, right across the border from Vienna. It was an old Russian plant, and they were interested in worker safety, so we made a badge that had gas sensors on it, would look at light levels and sound levels, but also we had a particulate sensor. That's kind of a smoke alarm that we put on. This is already in 2009. This is a video of what we did with it. So this is everything coming together kind of in a video panel. This worker here, the badge has a pressure sensor too, so we look at elevation. He's going up the lift. Here he gets too high, that's the threshold, and we can change the color. We can look at the gas concentrations too. This is more yellow, so there's more ozone over here. This one is bluer, there's more particulates, or volatile organics rather. So you can actually look in different ways on video at the state from this system. But now, sensors have gotten so tiny, we put it right at the bridge of the nose. So we can measure the quality of the air you breathe, just like we did in this big thing we did with ENEL 15 years ago. So we measure many different kinds of parameters, the air quality, light levels. We have a spectrometer on it as well. We even have a PM 2.5 sensor. There's a tiny one Bosch just came out with, and we're working with them. They gave us a bunch before they released them, and we can fit that up there too. So PM 2.5, in addition to all of this right up here where you breathe, it's intriguing. So yeah, a little more detail on the sensors that we have, a little more about how we sample them. My students love to have things show up in virtual worlds. This is a virtual version of the data. So. And we've used it in collaborations. We made 20 of them, and we're working with groups in Switzerland. There's a group in Fribourg and also at APFL, the Smart Living Lab. And we have a student from there that did part of her PhD with us, and she's been doing studies around the world using our glasses to see how buildings affect people. So we have a mobile app. It can display the data to people in different ways. We've, again, done it in many different places. And the app visualizes your data. So you're looking at your heart rate, you're looking at the different values of things it picks up, so on and so forth. We even can do what we did with our old comfort sensor on the Apple Watch, right? Are you comfortable or not? We get real-time information from that as well. This is one of the studies we ran. There are many of them. This is a very early one. We're still refining a lot of the data. Are you easily distracted when you're comfortable? Not really. When you're not comfortable, definitely you're easily distracted. At least what the data shows. We have to work on statistics. But here we're looking at when did you notice a color change? And it's changing here. They should have seen it. They didn't. When they're not comfy, they notice it. We even had to remind people when they're comfortable to get them to notice. So when you're not comfortable, you're distracted. And this is kind of transitioning quickly to smart textiles. I've loved the idea of having garments react as part of the HVAC system. And there are things you can do. My colleague Hiroshi Ishii has a fabric that he developed where if you get sweaty, it opens up by itself. It's like a big version of Gore-Tex, right? It makes these big pores. He used it with dancers. So as they dance and get sweaty and get hot, it opens up. We have other colleagues that are making liquid crystal fibers that can actuate and things like that. Can your clothing actually be part of the HVAC system? And in the same controller, so your clothing can heat or cool you in different ways, even with Peltier devices in the back of your neck or whatever, but do it with the HVAC system to save energy. So this is kind of another frontier that is exciting, and we've started to propose projects in this now. But one of my students is an adept at electronic textiles. Those are really, Italy has an important textile industry, we all know that. E-textiles really had an early start here. Media Lab was very early in the 90s, but also Daniela De Rossi and Rita Paradiso, a good friend of mine, but no relation. Some of you may know them. Real pioneers of e-textiles here in Italy. But the technology has advanced so much. You can do so much with textiles as a sensor in the built environment. So I'll give you a few quick examples of that. My student Ermindy does it in a knitting machine. He just knits conductive traces, knits different kind of piezoresistive weaves, and they can measure different kinds of things. And so off the knitting machine rolls a sensor, which is a textile. This is a keyboard he made, an early one. So this is me playing it here with my bad style. It's capacitive, so it knows touch. So it works. It's kind of fun. Not a huge deal, but it's a fabric. This one can change color, though. Threads are electrochromic, so we can change the color of the thing dynamically. But then I said, Ermindy, make me a keyboard that can measure everything. Non-contact, position and hover, touch, pressure, and stretch. And he did that. So this is part of his master's thesis. So here you can track the hands just with capacitive sensing, right? It's a conductive trace. So we know that. And then when you touch a key, we know that too. And if you stretch, we measure stretch. I know of no keyboard that measures stretch. This one does. And you can be virtuosic on it. So this guy is one of our better keyboard players at the Media Lab, and he can just go to town with it. So again, this is looking at different ways of measuring a user. A textile can measure lots of things, and textiles are all over our bodies and our environment. He's a better keyboard player than me. And Ermindy has also made thermal-formed yarns into things like slippers, where you have dense pressure matrices, a little wireless interface, a little row column interface with electronics. But yeah, you get dense pressure now from your feet in a wearable. This is another carpet that he made that came off the knitting machine that measures position and pressure really with centimeter accuracy. So this is a dancer. There should be audio. Do you guys hear anything? That's weird. Hopefully nothing broke. Anyway, she's dancing and there's music. Let's hope the next video is better. And then he made an architectural scale textile. He had a commission from Burning Man. I thought, do I want him to do this project of Burning Man? He was going to do it whether I said yes or no, and I knew it could be an opportunity, so I said go for it. He designed these himself. These are tapestries, basically. If you look at them, they have involved patterns he designed. Each one has a different cultural theme. These are the electrosensitive threads. So these can work with capacitive sensing. And he made it in Shenzhen. So went to China, made it in scale, went to Burning Man, installed it. And this is it at the Media Lab. Hopefully I have audio. Yeah, here you go. Here's a person in the center dancing. It's again capacitive sensing. We're looking at the electric field disturbance between the thing in the middle and each pedal. So it's a massive capacitive sensor as an architectural scale fabric. And he made a virtual version as well. So everything we do has something in VR. That's the Burning Man VR site. And I'm fascinated with this whole idea where you have basically fabrics or some stretchable media that has a sensor network in there. So it's not just row column where you have to connect up the edge. It's a computer network. And you just have the different processors network to each other, and you have sensors around them so they can measure lots of things, almost like real skin does, reduce it to features and route the features down so it's scalable. So it's a network in a fabric or in a material. So electronic sensor networks diffuse into materials. This is the time you're going to start to see it. This is a version he's making where it's actually cuttable. So you make this big thing with stretchable interconnects actually, all on flex, and you can put it onto a fabric and cut it and it configures. One of my students, Cedric, made a version on a line. So using technology in the LED industry, you can make a very thin line that's a sensor network with accelerometers, gyros, other things. And here he made a little glove with it. So it's tiny. You can actually weave these. He's weaving it. It's flat, but it's very narrow, so you can start to weave them. And we've flown them fabrics on the space station. This is beta cloth, a white cloth that lines spacecraft to give thermal protection. We're interested if you could put little piezos in to get micrometeorite impacts. So we put piezo fibers in there designed by my colleague at MIT, Yoel Fink, and flew it outside the space station for a year. That's it launching, that's it outside the space station. And we see what looked like real-time micrometer impacts, clusters of stuff coming in and hitting the thing. This could be the first indication in real time of these things. We know they exist. We know they happen. Now we're measuring them. We won first place in the NASA Tech Briefs contest for it. I'm almost done. Just another 5 minutes and I'll be there if it works. One thing that's really fascinated me for years is the whole idea of how people connect to these sensors everywhere in a way that extends perception, right? So we're kind of rooted in the here and now. Our phone kind of brings us to other places in a way, but what if we could have a more visceral way using mixed reality technologies to really give us the feeling of being somewhere different? Not necessarily giving us an image, but bringing that information into our perception in a way that really can enrich things. So this is the Doppel lab that I'm going to show. Basically, this is our building. What if you could see through the building and see all the sensors? See the sensors for the HVAC, which are these. Temperature, humidity in the atrium, people moving around. And just have a different view of the building. So this is something we did already in 2012. You can see the big spheres are not regulating properly. They're too cold or too hot, depending if they're red or blue. Blue is too cold. This is the temperature in the atrium. So you can see the color is the temperature basically, and you can see the humidity is a fog. These are people moving around. Actually, you can turn it up a little bit. So they have RFID, we can see them. We have other indicators of activity in the building. That's essentially the green thing that's bouncing. But we have microphones, and if you're near a place where there's a microphone in the real world and in the virtual world, you can hear through, but we distort it. So this is someone speaking English. Can't understand a word they're saying because we removed all the information. But we have the affect. So they're laughing, you can tell, you can get an idea of what's going on. So again, you see people moving around in events and things like that. We have several different versions of this that we made over the years. And yeah, then Negroponte comes in and that's the end here. This is a day passing in just seconds. So it's in setback, comes out of setback, and the atrium dries out, and people show up and kind of play with that. We call it digital twin now. Back then, there was not even a word for it. I was playing with it to extend perception. So this is the last thing I'm going to talk about. And this is kind of intriguing, I think, even for the stuff we're talking about. I'm going to give you a different kind of example. But user modeling is so important in everything, but it's going to be really important in energy use because you want to model users to forecast what they're going to do, but also try to approach them in the right way, offer the right incentives, and you know, figure out how to control the building. So we use different tools like we did with predictive mean vote back in our little wearable thing years ago. Les Norford is using graph neural networks to do it. But with deep learning, we're all going to have a digital twin. Google already is kind of building one, and Facebook are building one of us, but it's going to be kind of universal, and maybe one that we'll own ourselves. Ideally, we'll own our own high-fidelity digital twin that can forecast and anticipate kind of what we want and how we're going to react, and then use that for user modeling. We did it with music, as an example. We love music in my group. And does anybody know this guy? Jordan Rudess? Okay, a few of you do. There's some prog metal fans in the audience here. He's one of the world's most famous keyboard players, especially if you approach anything like progressive rock. He's won lots of awards. He was a child prodigy at Juilliard, just an incredible guy. Just kind of oozes musical ability. There's some people that do it. Jordan just is one of those people. And we're fortunate enough to work with him. We got him coming in as a visiting artist with my group this year at MIT. And we're looking at AI and music not to replace a musician, but to augment a musician, right? To enable a musician to do something, especially one as virtuosic as him, do something even more than they could do before, or ways to project their talent out in different ways. So we used a musical transformer model that was already pre-trained. One of our alums, actually, who became a researcher at Stanford, trained a transformer like what we use in ChatGPT, but one for music, looking at the notes to, kind of look at missing notes, predict notes, using that to train the model. She trained it on all kinds of music, so it's already pre-trained. It doesn't know anything about Jordan Rudess, though. So we fed the model hours of Jordan's playing, so it would kind of anticipate. It would be like a little bit of, we call it baby Jordan. It's like a little brain of Jordan Rudess, because we took something that knew about music, but really honed it on Jordan's style. So here in this example,
when I play with my right hand and I input notes,
the AI is doing the
it's
accompaniment.
the model's job to kind of look at what's going on with my right hand.
It's
So
playing
if I
the
play,
bass line and it's playing the chords. And it's taking,
and I
it's playing
introduce
as
the minor,
guidance.
and we can listen for when, and in this case, maybe if it's going to pick it up. Give us some more info. There we go. So I played in minor, and I heard the bass line actually address that minor note, which was the da, right?
So here he is just going to town, doing what Jordan does. So he's doing the lead, and the AI is listening to what he plays, it knows his style, and it's doing the bass line and the accompaniment. He's not telling it to play those chords. It's just anticipating it based on what it knows from him. But we went further. What if we could do Jordan's leads? Because his leads are world famous. The guy's just incredible. Now, I can play some keyboard. I can't play like Jordan. I dream someday that, if it's kind of late, I don't think it's going to happen. But look, what if I had Jordan working for me and I could just play the chords and kind of drive Jordan in certain ways? So we did that. We modeled Jordan's leads. He gave us a bunch of leads that he played, built into the model. And here's me. So I'm just playing chords and it hones in. Resolved very well. So that's another kind of user modeling. And it's pointing to an incredible future. We can take the essence of someone who's really good at something like Jordan, a virtuoso, and put him kind of into a box. And if I want to put Jordan into my tracks, if I'm composing some music, I can just bring him in as a plug-in and have a Jordan lead I can paint a Jordan lead over my music if I want. So we're getting into that. And you don't even have to be alive for this. That's the amazing thing. So anybody here know Marvin Minsky? He's one of the pioneers of AI. He was a close colleague at the Media Lab. He passed away about 5 years ago. He didn't see true AI, so he knew it was going to come. He was talking about it forever. one of the people that really put AI on the map in general. He was a pianist, and he would improvise fugues, and this is a version of Frere Jacques he wrote, but he'd usually do fugues. And he would just play them and he'd record them on his tape recorder, reel to reel. And his family gave us access to really hundreds of tapes. And students digitized them so we can build a model of Marvin Minsky's piano playing. This is somebody who unfortunately we lost 5 years ago. We only have his recordings. And we have Marvin coming back. This is Xiao Xiao. She's actually an alum of the lab who's now running a research group in Paris at the Da Vinci Institute, but she came back to visit us for a while, worked with my student Lancelot to bring back Marvin with that model. Built a model of Marvin's fugue playing, and here's Xiao prompting it with a little bit of fugue playing, and then Marvin's ghost. It really is his ghost. This is the style of Marvin, plays back. He learned from listening to the tape recordings. Continues what she did because it has the mind of Marvin, musical mind of Marvin. So it's just an incredible world here. Anyway, looking forward, future energy is going to come from fusion and safe fission, I believe. This is the goal. This is one of the things that will help get us there, and renewables as we get them. But no matter what they are, we can't scale them in time. Again, we've all said it. I agree totally. We've got to dial down usage in the interim, and information from IoT sensors are going to be crucial here. These sensors are embedded, of course, everywhere in every different kind of way. I've given lots of examples that are a bit unusual here. We're going to leverage AI controls, user modeling in ways I've hinted at here as well. I'm sure some of the other speakers have spoken about it or will. And estimating elusive parameters like user comfort, really. We're going to get closer and closer to how we feel about places and trying to incorporate that in the control systems. So thank you very much.
Of course, thank you so much. And what again impressed me is the sense of freedom, which means being free to think and to explore. And this is what touched me, and I think it's really amazing. And I really envious not to be able to be part of it, but thank you so much for bringing this to us.
Always a pleasure to do that, and it's
amazing.
Yeah, it's a privilege to be able to be at a place like that. I mean, Xerox PARC Bell Labs, they're in places that have been free, and they've had great people do great work. Media Lab, look, these places I hold in very, very high regard, but yeah, we have something of that in it, and that, yeah, we're lucky that we can kind of dream up an idea and do it.
The point is,
great students.
From our perspective, we normally have to do things, we as a business company, but I really hope that for everybody is the chance not to just think in the short way, but to make a big jump, have imagination, because where we can get, there's a lot of technologies, possibility, more than we know what that we have in our hand. So this part of freedom is really special. So thank you for inspiring us.
Thank you. And I think what you guys are doing is very important to make it real. And at the Media Lab, we treasure that too, because our industrial partners that work with us and translate some of these ideas. Plus our students do the startups, so we're very entrepreneurial. So yeah, we do believe in getting it out into the world. I'm more the kind of guy that likes to think, what other wild thing can I do next? But yeah, we do value that importance of trying to get the stuff out. That's hard.
You can also have fun sometimes. That's pretty good too.
That's always a side benefit. Thank you.
Ci sono domande dal pubblico?
A problem that for us maybe in Europe is more important is that every time that we try to implement such IoT systems, this kind of implementation on field with real clients, there is always a big problem of privacy, because people don't like to be monitored, no cameras, no microphones. So how can we overcome this limit and to have something useful?
I think that's one of the deepest questions of our time, because it's true, these sensors are out there. In my house now, I think I have 150 IoT sensors probably. They're all from different companies and they're kind of balkanized, but they're there and the streaming data somewhere. It comes down to trust, right? So you, at some point, have to trust that nobody is going to use this in a bad way. How can you verify that? You have to verify it by having some encryption. You have to be able to maybe own your data. You probably know of Shoshana Zuboff's book, The Age of Surveillance Capitalism. I have a chapter devoted to me. Not in the nicest way, but it's a good book to be in. This Doppel Lab that basically got her going with that. I think it's really kind of crucial that we have some way of encrypting the data, owning it. It's not stuff that I do as much, but Sandy Penland at the Media Lab is very involved in that. He did the whole New Deal on data and stuff like that. He works with Ron Rivest and other people that work in encryption models. So I think that's one of the most important things, where you feel you are somehow in control. The data is streaming to some agent you trust. It's encrypted probably at the source. And you have some control over where it goes. Now there's so many, we just give our data away because we just click yes and we don't care. But yeah, there will come a day when this could be a deep issue and people get more sensitive about it. US less so than in Europe. Europe, you've always been sensitive about it, and I think the concerns are very relevant and germane. And as soon as something bad happens with this stuff, yeah, people are gonna wanna have more control over it. You know, years ago, we put cameras all over the Media Lab. We did a whole thing with cameras, they were in the infrastructure, lots of other sensors, and we did we used as a lab, lots of different explorations of different ideas, a whole separate talk. People didn't like it. I had to give a lecture on how to disable them. I had to put a big switch on them to turn the camera off. And then after that, you know, we took those all down, we put up Kinects. No one cared. They didn't see it as a camera. So they lost their fear, even though it's every bit as much a camera, even a better camera than what we had there. So it's also in the way attitudes change, acceptance of different kind of a platform, how you actually show what the technology is doing. But I think in any regard, it's still a concern and you want to be able to control it.
Ci sono altre domande dal pubblico? Vediamo. Altrimenti, Luigi, ti ridò la parola per un saluto finale. Un applauso, allora andiamo a chiudere il pomeriggio. Thank you very much. Thank you. Grazie.